Cool. So this Unit 1 and 2 class, we're going to be having a look at some of the fundamentals of the functions and relations stuff. I'll go through the main content here. If it ends up being the case you're still the only person in the class, we'll then move on to if there's anything you want to specifically have a look at. That way it can at least still be more relevant to whatever you're currently doing at the time. But okay, so first up, set notation. What is this all about? Mainly you're going to be using this when describing domains and other related things. So a set is just simply a collection of items of which a collection of x values is one such possibility. We call that one the domain. Stuff like x is an element of A, you'll have these little symbols to denote that it either belongs to the set A or does not belong to the set A, depending on whether or not you have a slash through it or not. You can also do that with the set difference symbol, this backslash, so it says everything in A but not in B. That's way more common of how you would describe things, but you do also have the possibility of just saying X does not belong to any of those that belonged in A. The other thing that exists is this idea of a subset. So basically the whole idea of a subset is that you have a larger set of numbers that is denoted A in this example, and within that set is another, is described as another set within that. So all the elements of B exist in A, but it's not necessarily the case that all the elements in A exist in B. The way you would denote subsets is with the symbol here, like that sort of inverted U type thing. And you do it in the order of smaller to bigger, basically. So B is a subset of A. Most of this is just going to be notation, then we'll move on to the functions relation stuff. This will be more useful for when you start getting into probability, but also somewhat in your domains and ranges as well. The intersection is going to be whatever's common to both sets. So when you had like the subset, for instance, the intersection would just devolve all the way down to just the set B, because everything in B is common to A. But when there are elements that belong to only A or only B, then yeah, you're probably going to likely have some bits that are intersecting as well. That's denoted with the intersection symbol there. If there's no intersection, so that is to say your Venn diagram is fully apart, you would write it with like this, basically a 0 with a slash through it, which is described as either the null set or the empty set. Those are also referred to as disjoint events or sets if they have no intersection. And I believe the last thing in this section here is going to be on the sets of numbers. So there's a whole bunch of different double-stroked letters that you'll come across when it comes to maybe domains or ranges, namely. And it's important that you understand the differences between them. So the most common are going to be the natural numbers and the integers, the n and the z there. So as long as you got those two mapped out as to what they mean, then that'll be the most important bit. And then we also have some other things that are worth understanding what they are, but you won't necessarily see their symbols. You only really need to know what they are based on like prerequisite information in the question. It might say, solve A and B, where A and B are rational numbers or irrational numbers or whatever that is. Knowing what that means would help you more or less get a better idea of what you're aiming towards. But okay, so the natural numbers, you can basically think of these as the things you count in the real world, right? You never go negatives, but you're always basically counting in whole numbers when you're counting some number of objects, right? 0 is included in the natural numbers, and that's denoted by this double-stroked n type thing. Then you've got the integers. So the integers are basically the natural numbers, but you can also go backwards into negatives, and that will be denoted by the double-stroked z there. So those are the main two symbols you need to know the difference between, because that'll be important for your domains and ranges. These ones more so just sort of nice to know. Rational numbers are essentially fractions, a over b. Now, there is a bit of a nuance here. Not necessarily always a fraction. Rational numbers is actually contained within the integers and natural numbers as well. simply because sometimes your denominator is a factor of your numerator. So something like 4 over 2 would be a fraction, yes, and therefore a rational number. That also simplifies down to 2, and because 2 is the same thing as 4 over 2, therefore it is still also a rational number. So rational numbers basically is the same as all of this, but it can also be a fraction. Irrational numbers are those that cannot be represented either by a fraction or by a whole number. These are going to be like your special things like pi or e, and even some of your roots as well. There's no given letter for it, and even this letter Q here is, I don't think, used anywhere in methods. If you want to describe like what that set actually contains, it would basically be all possible numbers excluding the rationals. Whatever's left over is the irrationals. So yeah, those special numbers, those are basically like your infinitely extending decimals. They'll never actually terminate on a particular value, and those are just a couple of examples of such. Real numbers, this will be like the most common thing you'll see by far. Double stroked R, it's just everything, right? As far as methods concerned, anyway. Technically, for those who are doing spec, you also get into the imaginary numbers, which exist kind of as a kind of perpendicular to this whole sort of arrangement. But as far as methods goes, you can just think of all real numbers as just any possible number that you could think of. And there's basically a hierarchy, right? So as far as like the size of the sets of numbers and how they're related to each other, you've got the natural numbers, and within that is the integers. Within that, you've got all the rationals, and within that, you've got all the reals. So they're basically like a sequence Russian nesting doll of the possible sets. That's more so just a bit of a refresher on the notation side of things. Is there anything that should be clarified further regarding that? It's very much more so just, hey, you need to be able to recognize what this is talking about, rather than there being a question around it. Cool. Okay. Onto more so the meat of things. This is where questions do actually get asked. Oddly enough, even in Unit 3.4, I think some multis will even ask questions about some of the basics of functions and relations, namely what is a relation, and we'll start to also look at how you can solve for domains and ranges. So we normally think of functions as like our rules, where you have like y equals mx plus c, some sort of quadratic maybe, or a polynomial, whatever the function is. We literally use the word function to describe that. A function is actually a subset of a bigger term called the relation. And a relation is also very similar to a function. It belongs in the set of relations, but there's less restrictions on it. So relation is just any relationship between sets of variables. So the most basic is something like y equals x plus 2, right? You've got a relationship between the y and the x. Y is always just whatever x is when you've added 2 to it. Very simple. You're not restricted to 2 variables, and what those variables look like, what they have attached to them, also has no restrictions in there. As far as the kind of expressions you might start seeing, this is valid notation. Basically, whatever's denoted at the very front will be whatever the ins and outs of the function is, or the relation is rather. So basically y you would always sort of consider as the output, the thing that goes on the y-axis, and whatever's on the right-hand side is usually considered the input, the x-axis. So you've got your x and y, denoting that those are the variables that actually exist. It might seem like it's being duplicated, because, why wouldn't you just look at the rule? If it's not listed here, it means that any other variables or letters that exist in this rule aren't actually considered variables in that case. They'd be considered constants. So if I chucked an a in here, but there was no a that appeared in this list, a is not actually going to be a variable in that case. It's going to be some sort of constant or coefficient that you're required to find. So that's why, even though it seems like that's sort of duplicated, this does actually kind of matter a little bit for interpretation of what you're actually doing. And then the last bit is going to be the domain. So all the possible x values or if, for whatever reason, you have a more complicated thing, all the possible inputs to your overall relation. For methods, you're only ever going to have two variables with your given functions or relations. But it's worth pointing out, even in Spesh actually, in Spesh you look at things called, I think parametric equations do this, where you essentially have things across three separate variables. They work a little bit differently, but there is precedent for having different, more than two variables in your function. Okay, just basics on domain of range. We should already be familiar with this. Domain is all the possible x values, or more generically inputs to your relation. And the possible outputs is considered the range of your functional relation. Typically we're using interval notation or set notation. Set notation is like this sort of stuff that we were looking at earlier. Interval notation is this stuff that we're looking at here, both of which are valid. And oddly enough, one sort of contains the other. You can see we're using some set notation stuff here. This is where you start actually getting questions that you now have to solve. So this sort of stuff is all good to understand the basics of the question that you're given. This is where we start actually being able to solve some things. So for whatever reason, finding maximal domains has consistently been a bit of an issue for, I've just seen it become a bit of an issue for a lot of students that I've taught. So what I've basically done here is go through all of the possible functions that you'll come across in your in methods and what their effective maximal domains are going to be. And if they aren't just real, all real numbers, how would you go about doing that? So the keyword maximal, as far as domain is concerned, just means what are all the possible x values that could fit in that function or relation without, if you didn't manually put a restriction on it, as opposed to just any old domain, which can be any subset of all of that. So for instance, linear, there's no like restrictions as to what can go in the x spot. If you have y equals mx plus c, any x could go in there, positive, negative, zeros, whatever. But a possible domain for that could be 0 to 2. You are allowed to restrict within all the possible domains that could exist for that function. So maximal domain is just as big as it could possibly be and no bigger. You'll see there's only a few types of functions that do have restrictions. So linear, polynomials, exponentials, these are all fine. They're defined over all real numbers, even the odd root graphs. So that'll be like your cube root, fifth root, that sort of thing. It'll be the logarithms, it'll be tan, your hyperbola truncus, and your even roots. These are all going to have restrictions. As far as what those restrictions are, most of the time it's going to be based around either asymptotes or anything else that breaks the math in some way, shape, or form. Like for logarithms, we have vertical asymptotes, right? And that's set at wherever the horizontal translation term is. Or in other words, if you think about things purely in terms of the function, logarithms cannot actually have 0 in the brackets, or negatives for that matter. So when we're thinking about what the maximal domain is for a logarithm, that's what we're solving against. We want to make sure that whatever's inside that bracket, literally whatever it is, has to be greater than 0. Because logarithms won't ever have a 0 in there or a negative. Otherwise they become either undefined or non-real. So all you do is literally put that as an inequality and solve that inequality. I've given you a linear example here, which is super easy to solve, just knocking things over to the other side. This might be a quadratic. This might be an exponential. This might be a God knows what. It's still just going to break down to make whatever's in the brackets greater than 0. And if you do have something more complicated, usually, rather than doing the actual algebra, it's typically best to graph whatever's in here first. With linear, there's no effort really required. For quadratics, suddenly you have to worry about what happens when I square root when I have inequalities. You get into sort of issues like that. So it's typically better to sketch whatever's on the inside if it's more complicated than linear. That's a fairly basic example there. Is there anything that needs to be clarified so far? Okay, next up, tan. So tan, actually maybe I should be showing the pictures of the graphs as well, just so we can all be on the same page. So for that logarithm, let me just quickly grab a picture of that so you can sort of see why what was going on was going on. Or not. I got the other one. There you go. So this is what your typical logarithm will look like. It's got a vertical asymptote here. It'll never actually approach, nor will it go over to the left-hand side of the graph there. So knowing what your graphs look like can also be quite helpful for solving maximal domains. The other one of which comes up with tan. So tan is also a bit of a funky kind of graph, which has a few implications, namely that it has a bunch of asymptotes involved. It's a bit different to the sine and cos, because tan is the division of sine divided by cos. So when you have division in functions or relations, one of the possibilities is now asymptotes, or more specifically vertical asymptotes. Does anyone remember why you get vertical asymptotes from division sometimes? Think about any a divided by b, and you're sort of stretching that if your denominator is the variable. There are certain denominators that break math a little bit.
0.
Yeah, exactly, 0. And whenever you divide by 0, there's no actual value for that. It's undefined. And the reason why you can't just choose infinity, for instance, because, like we have this sort of intuitive idea of, okay, well, if the denominator gets smaller and smaller, the number should get bigger and bigger, right? Like 1 divided by a half is going to be 2, 1 divided by a quarter is going to be 4. We're getting bigger and bigger. The problem with that logic is that dividing by negatives and going to 0 is also valid, right? Dividing by negative a half gets you to negative 2. Dividing by negative a quarter gets you to negative 4. So just as it's possible to shoot to positive infinity, it's also possible to shoot to negative infinity, which is why we give this undefined rather than plus or minus infinity. And what that appears like on a graph is an asymptote, because from one side you're shooting off to positive, on the other side you're shooting to negative, and there's no clear distinction as to when it should transfer over. So because of those asymptotes, we just need to figure out basically where are those asymptotes going to occur for our tan graph. And that is going to be our restriction on our domain. Everything, all x values are possible, except for where we have asymptotes. There's a few ways you can do this. I know the book has actual tan asymptote equations, which are similar to like your general solution stuff, if you guys have done a lot of your circular function stuff yet. My preferred approach, rather than memorizing 2 separate equations for it, because tan actually does have, if you do the equation route, 2 different ways of doing it, depending on what you have it here. It's a bit of a simpler approach, in my opinion, to only have one way of doing it, which is splitting tan into sine divided by cos. So tan by definition is sine divided by cos. Whatever's in the brackets is maintained. As we discussed, asymptotes only ever occur, or vertical asymptotes are occurring, when we have divided by 0 errors. So now the whole thing simplifies to just figuring out where does cos go to 0. And this is something you do need to know, both Unit 1 and 2 and Unit 3, 4. So that way, rather than you guys having to remember 2 separate new equations just for tan, at least this way you can go back to your sine and cos stuff and solve it that way. If it's been a while, actually, does anyone need a refresher on how we solve circular functions? I'm happy to take a detour here, because this is going to be a pretty short chapter. We got time. Sweet. Yeah, so where does cos go to 0? Well, you're just looking for all the x values equaling 0 on the unit circle. But because there's no, the whole idea is finding the domain, you're not going to actually have a restriction here, so you've got to give it in general solution terms. So basically, if you think about where the unit circle would be for cos, x being 0 is going to be the 2 vertical spots at pi over 2 and negative pi over 2. Or you could do, for instance, pi over 2 and 3 pi over, and 3 pi over 2. But because you can go around the unit circle multiple times, you also smack on this plus 2 pi n term. And yeah, that's going to be about it. This is just sort of me demonstrating that you can also simplify things a little bit further when it comes to cos because they are vertically separated from each other. Oh, sorry, actually, no, it's not. This is me rearranging things. Never mind. You want to get the x on its own. My bad. So basically, you want to add pi over 2 to both sides, and because you get to a stage where the plus and minus cancel out on this side, and the plus and minus add together on this side, you've got 0 plus 2 pi n, which is just 2 pi n. Pi plus 2 pi n it basically just simplifies down to pi n here, because pi n is a factor of 2 pi n. Pretty normal for tan, because any two given tan solutions are going to be diagonally opposed from each other, which as far as unit circle is considered is pi separated. Now, this isn't necessarily good enough as a final answer, just saying x equals pi n. You kind of want to jazz it up a little bit. Not only do you have to give it in your either interval or set notation form, but you also have to actually define what n is if you want to get like full marks. Your SAC, your teacher that runs the SAC might be a bit more lenient with you defining what n is. So maybe just this, you would get away with it perhaps, but if you want to go for full accuracy, you should also define any variables that you're putting in there, even if they are very consistently used in the book. So how we sum everything up, the whole idea was finding the asymptotes. So we just got to say that x can be everything, all real numbers, excluding what we just found, given that n is an element of the natural numbers. Natural numbers? That should be integers. That needs a fix there, because n can go negative as well. Yeah, so we should be using the other one instead, the z double stroked. I'm going to put a reminder there to fix that up. Z. Cool. Any questions there? This was sort of diving into the circular function stuff. All that making enough sense? Hyperbola is going to be very similar, except there's no circular function stuff going on. Its denominator is a lot simpler. So the hyperbola, just for sake of refreshing, the hyperbola looks like this. So again, you get that vertical asymptote going on, but because the denominator is a lot simpler, it's only going to have one possible spot where it goes to 0, right? X equals 0 in this case. Or if you have some transformations involved, like this one, shifted left by 3, well, at this case, when x equals -3, you'll now have the asymptote, because that'll make it go to 0. So again, literally just denominator equals 0, and once again, making sure you put that in actual domain notation, rather than just saying x equals -3. We're trying to find maximal domain. Truncus, exact same idea. All right, still just a denominator, even if it is squared. If it is squared, sometimes... No, actually, this should never really be an issue. You're probably not going to get your plus minuses, because the truncus only ever has one vertical asymptote. So it's still just the same thing, but you're dealing with a quadratic as opposed to a linear. But even then, it's really not that bad, because you're square rooting 0. So you're not too fast. This is where I can start putting a bit more nuance on the functions. So even roots, that's going to mean your square roots, your fourth roots, any root that has an even number attached to it. All of these have a starting point. They have a vertex. And so anything behind that vertex is no longer valid. You can take the root of 0. You just can't take the root of a negative number, more specifically the even root of a negative number. So when we do our solving for this, it's a little bit different to the logarithm. For the logarithm, we were greater than 0. For the root, specifically the even root, we're going to be inclusive of 0 in there as well. So it's a very, very small difference, but it does matter, because this will get you marked wrong if you don't include the 0 in that. The reason why I've given a sort of generic approach to all of these rather than giving you specific ideas for each function is because sometimes you might get some stupid shit like this, where you just go, okay, there's a fraction involved, I've got a root, I've got a log, what's going on here? Well, you're basically just looking at the nuances of each individual function, what's it restricted by, and one other thing to also consider is going to be if there's fractions involved, divide by zero errors could also be possible. So keeping all those things in mind of all those examples, we're just going to sort of tackle it one at a time and then see what goes, and then see what the intersection of all those things is going to be. So in this case, I'm starting with the root. Well, root can only ever be positive or inclusive of 0, so let's make sure that's the case. Grab whatever's on the inside of the root, make it greater than or equal to 0. Step 1. Next up, logarithms got some very similar things. Remember, we want it to be just greater than, not equal to 0. And once again, yeah, just grabbing the inside of that logarithm, seeing where it's greater than 0. Last up is because there is division, there is potentially possible for a divide by 0 error, so let's figure where out that is. Natural log can't equal 0. We're just going to solve that via the flip to exponential. Does anyone need a refresher how to flip between logs and exponentials? Yeah, so just flip that exponential form and figure out what the restriction is there. Just be a bit careful of how you do these. So what you might notice is both of these were written in terms of what is valid. This one here was written in terms of what is not valid. So when you're combining all these things together, just make sure that you either keep them all the same, of all being inclusive or all being exclusive, or yeah, just making sure it's very clear what's going on there. As far as getting the intersection of all these things, you literally just plot them on a number line and then just see where do they overlap. So x greater than or equal to -2 is the red. The other one's over there. They're obviously just going to overlap there. What we're going to do is make sure we're also excluding the 2 from that. So how you would solve this or finish this up would be something like this, using your rounded brackets because you're non-inclusive of the 1, shooting off to infinity, and excluding 2. The TI-Nspire will actually give this to you. I don't know if the Casio... Oh, yeah, I looked this ahead of time. Casio doesn't actually have this, so only those who are using the TI-Nspire. This will not be something you'll find in the menuing. I think you'll have to literally type out domain or use the book feature. So I'll just pull up the CAS real quick. You've got the book feature, which is this one here, and you should be able to... I've actually got a default there already. If you just hit the letter D, it'll take you to the top of the D options, and then you just, I don't know, click through until you find your domain that you're looking for. Or manually type it out, right? It's also perfectly valid to literally type out the words. You'll know you've got it right when it goes no longer italics. And yeah, actually, we might as well do a live demo there. So you will get the exact same thing that I've written there. Let's give that a shot. Square root of x plus 2 over natural log x minus 1 comma x, and well, you're going to get it in their notation there. You would want to tidy that up a little bit. This is like saying what could x be equal to. When you give your domains, typically when I give it in either interval or set notation, which is the green highlighted that I've got going on there. That'll be the main thing, really. Is there any questions as to how that's going on? Because if not, we can do some textbook stuff. Or otherwise, if you guys are cool enough with how this is going, because it is a fairly self-contained little thing, is there anything you guys would rather go through if this is all good? Cool. Let's do a bit of practice then. And then if you go sick of it, we can do other stuff. Okay, let's see. Domain range. Domain range. Where's the maximal domain stuff? Here we go. Yeah, here's some maximal domain stuff. Let's go with question 8. My notes real quick. Okay, let's see. They're all pretty similar. Start with the hyperbola. Y equals 2 over 2x minus 5 plus 3. We're going to give both maximal domain and the range that will be associated. Let's see how we go. What are the restrictions involved as far as hyperbolas are concerned with maximal domains? Oh no, I've bored everyone to death. Yeah. Something specific around division, right? So division always has some potential issue with it when you have variables involved. What potential issues could come up that would break math as far as division is concerned? Yeah, divide by 0, exactly. So divide by 0, the possibilities there basically just mean you now set your denominator to 0. 2x minus 5. And well, this is linear. 5 equals 2x, x equals 5 on 2. Cool. Easy. They do have some other funkier graphs going on here. Like you might have noticed, they have like the x squared plus y squared equals 9. They've also got this thing in 8f, where they've got squares on the y. These are graphs you're not necessarily required to be able to do in methods. They are in there, but it's not actually in the study design. I don't really know why they still... Well, I know why I've put it in the study design for my thing, just because it sort of helps out a little bit with understanding why the root looks the way it does. But as far as being able to interpret and sketch these graphs, that's not required here. So as long as you're cool enough with how each of those individual graphs look like, that's really all you'll need to know. Any more of these you want to practice? You are now the last survivor of the class, so if there's anything you wanted to have a look at but didn't want to mention, now would be the time to do so. Like, what are you up to currently as your studies? Are you still here or you're muted? Uh-oh. Holiday mode, sure. Maybe like a thumbs up in the chat if you don't want to. Oh, mic won't work. Sure. Gotcha. Well, what topics are you up to? We can have a look at that instead if this isn't too helpful or relevant right now. You've already done all this? Yeah, sure. So what are you up to? What are you up to currently then? After what'll be like the next things? We can have a look at that. But for context, I can hold the chapters out as well. So that would have covered like your chapter 5 stuff. Oh yeah, gone on to polynomials, sure. let's have a look at that then. Do you have any memory of doing anything polynomials related, or should I just sort of start from the beginning more or less? Start from the beginning? Yeah, absolutely. No worries. Cool, cool. Okay, let me pull up some polynomials. And close a bunch of tabs. So, polynomials, what's going on here? Polynomials are an extension of linear, essentially. So we think of linear as your y equals mx plus c. You've got a coefficient, a variable, and a constant. Polynomials is when you start getting powers involved on those x terms. So not only will you have the linear portion, cx plus d in this case, but you might also have a power, like x cubed or x squared or whatever. These are what polynomials are. They are just a sequence of x to the power of something, and they may or may not have coefficients attached to each of those terms. One of the key phrases you'll need to know for polynomials is the degree of a polynomial, which is essentially just whatever the highest power is on your x term. So if we look at this f of x here function, the highest power in there is 3, so this will be considered a third degree polynomial. That's the gist of it, really. As far as how you go about solving polynomials, as soon as you have anything above linear, whether it's x squared, x cubed, or whatever, things get a lot more complicated to solve. You may or may not have done, you probably would have done quadratics at this point, yeah? It'll be similar ideas where you can't just rearrange things on either side. With quadratics, you can kind of get away with it. If you write it in a very particular form, you can just get things rearranged. But anything, and that's, yeah, no, you can do it with all quadratics. But anything above a quadratic, you'll have to definitely do a lot of different approaches. The main approach as far as methods is concerned is going to be via a factorization approach. So you would have done this in quadratics. Maybe just a quick yes or no, you've done quadratics before, yeah? Yeah, sick. So factorization you should be familiar with, and the null factor law you should also be familiar with at this point. But as a refresher, basically it just means whenever you have a product of two things, any sequence of brackets that equals 0, either one or the other of those brackets must have been 0. Right, like I could have 2 times 0 to get me 0, or I could have 0 times 2 also get me to 0. So what that looks like as far as algebra is concerned just means you grab each of those terms, make them equal 0, and then solve them. So nice and simple. So whenever it comes to actually solving things, you'll either already have it in this factorized form, in which case you're really happy, or you'll have it in something like this and have to use supporting information to get it into a factorized state. As far as the nuances around how things work, it might be linear, it might be linear quadratic. Basically, whatever's in here, you just solve it as if it's its own individual thing. So the x minus 1 goes to 0, and the quadratic goes to 0. How do we solve quadratics? You've got so many ways of doing it. You could factorize, which would be the fastest way, doing your add together times together. Two things multiplying to give 1, adding to give 2. Well, that's just going to be 1 on 1. You could do quadratic formula. You could complete the square if you really wanted to. Be a bit of an ordeal though. But yeah, whatever method you prefer to solve with quadratics, you can use to get that solution there. It may or may not have one solution. Usually it'll have 2, but this will end up being a perfect square. Sometimes it doesn't have a solution, in which case, those sort of things of doing your quadratic formula start to become a bit more viable because they can tell you ahead of time whether there even is a solution to it. More specifically, you can shortcut things even further by using the discriminant. So that'll be the b squared minus 4ac, that term that exists in the square root. If that ever goes negative, there's no solutions because otherwise the square root would become negative, which we talked about at length with our maximal domain stuff. Square roots can never have a negative in there. And yeah, because the discriminant's negative, basically what that means is this term contributes nothing, and the only solution for this polynomial is going to be the x equals minus 3 that came from here. Cool so far? Anything I should clarify? Sweet. Okay, next up. So this isn't necessarily solving polynomials, but it is another thing that comes up, which is trying to figure out how to go from one look at the function to another look at the function. So we're told in this question that f of x and q of x are the same thing. All right, they're equivalent. And based off of that, we have to figure out what a and b are. They don't really look the same, but they're close, right? They got like this plus 8 involved. They both got an x cubed term. What do we do from there? The way polynomials work is essentially because these are the same thing, we're told these are the same function, you can basically just go term by term and see what the missing link would be. Like for instance, this is ax cubed, this is 4x cubed. Therefore, a should be 4, right? You're just marrying it up. Where it gets a bit weirder is where terms don't exist, right? This one has an x squared, this one does not have an x squared. This still does work out though, because it just means you put 0 in for b, because that will delete the term entirely, make it disappear. So just keep that one in mind. And obviously, well, a is going to be equal to 8. There's no point marrying those up. You've already done what you need to solve the a and the b. That's more of a bit of a fundamentals thing to just get you with the idea of it. Much more common, it's going to look like something like this, where you've got quadratic and you've got also quadratic, but it's going to be the completed square form or the turning point form, depending on how you phrase it. Same question. These are the same. Now find a and b. One of the challenges you're going to run into here is that they're not directly comparable. Right? Like this plus 14 doesn't necessarily go straight to that c because the format is different. Right? There's no x term in there, there's no x squared term in there. So you have two options as to how you want to handle this. They both stem from the exact same principle, which is make both functions look the same. Make them into the same form. You can do that by completing the square on this one, and then that'll make them directly comparable. Or you could expand this, and then that'll make them directly comparable as well. When in doubt, probably just do the one that has the numbers in it, because if you start expanding this out, like, it's not technically hard, but I know people get a bit yuck when they look at a bunch of coefficients and like, oh shit, what do I do from here? Expanding this out tends to be harder than working with pure numbers. So my recommendation is stick with the numbers where possible, but try to practice both just so you can, because you still do need to have good algebra fundamentals. I'll give them both examples here anyway. I do also have an equation for completing the square. You and everyone else has probably learned it with like a method where you halve the b term, you take this a out, you distribute it back through, you got your whole halve it, square it, all that sort of thing. Are you comfortable enough with how you complete the square your way? Because if not, there is a formula you could use instead if you wanted to know. Yeah, let me know and I'll put, oh, you're all right? Yeah, sure. So yeah, just completing the square. If you do it, you'll get down to this stage here. F of x has been converted from the quadratic to the other quadratic. And now when you look at the comparison between those two things, you can say, oh yeah, well, there's an a there, there's a 6 there. A is going to be 6. There's a minus 2 there, there's a plus b there, so plus b should be minus 2. There's a minus 10 here, there's a plus c, c is going to be minus 10. Here's the other approach if you're interested. So again, directly comparing them, but this time you're expanding that right-hand side, x squared, b squared, and then the combination of the two, distribute that a all the way through. And this is similar to here, where we had this sort of thing going on, where you just go term by term, equate the two things together. So for instance, ax squared, 6x squared, a is 6. Where it gets a bit weirder is keeping track of what's x squared, and what's constant, because you'll have a bunch of letters involved. So you just got to make sure that anything with the x is considered the variables. In that case, those are the things you're comparing, not just letters to letters. But otherwise, it's the same idea. So that's your fundamentals of polynomials. They are just a sequence of x to the power of n terms, and the quadratic is one of them, right? It's a second degree polynomial. How we solve them is typically going to be using your factorization and null factor law techniques, of which we will dive into more of those factorization techniques. In fact, we actually have time more to look at them as well. So let's get you introduced to that as well. So we've already discussed that when it comes to solving polynomials, you can't really do a whole lot with if they're in their cubic form or anything above. We're going to get them into a factorized state. How do we do that? We do that with a technique called polynomial division. I'll get into the nuances of how you do a polynomial division, but for now, let's just consider the idea that, basically put, you can take a fraction that has polynomials involved, right? In this case, it's a third degree polynomial divided by a first degree, or a linear, and out of that you'll get a quadratic, right? You can kind of think of it as the x cubed being divided by the x to get you the x squared, and then a bunch of other math magic will happen to get you the rest of the terms. This idea of being able to convert a fraction of polynomials into a simplified state is important, because if you look at what this actually is, that's essentially just an equation, right? It's saying this is the same as that, yes, but it's also an equation. So technically, you can multiply both sides by x plus 2, and that would get it into a factorized state. You'd have the quadratic multiplied by the linear. You've essentially converted this cubic into a quadratic and a linear as a sequence of factors, and that basically gets you to, where is it? That gets you to this stage here. We have a linear and a quadratic, and you're solving via null factor law. So that's why we even bother doing this in the first place. As for how you do it, it is quite a sequence. Looking at this the first time is usually quite tough, so we'll go into detail here. Probably going to be especially tough if you can't also talk as well, because usually we'll do it live, and I'll get students to basically say the steps as we go. So I guess we'll have to settle for now for just sort of going through it together like this. But okay, so how do we start doing this? You can use polynomial division whenever you have a polynomial divided by another polynomial. How it works. First up, you set your division up. Denominator goes at the front, numerator goes in the middle. This is a very similar, if not identical, algorithm to how you do regular long division. I was never actually taught long division. I don't know if you were, but it is the same sequence of steps that you do. First up, take the highest order or degree terms in the sequence and divide them by each other. That's it. So this is the biggest term here, this is the biggest term here. X cubed divided by x. It's always inner into outer. You can do some working out on the side if you want, but if they're simple enough, feel free to just chuck it on the top. So basically, x cubed divided by x is going to give us x squared. That's step one. Step two, grab that result, whatever that is, and multiply through by the entire denominator. So you grab that x squared, multiply by x plus 2. You'll get to a stage where you can definitely do these in your head. X squared multiplied by x gives you x cubed. X squared multiplied by 2 gets you 2x squared. If you want, you can also, again, go to the side and write this out manually. This is more so just so you can see what the arithmetic actually was, rather than what you would actually do when you write it out. The result of that is going to be placed underneath the polynomial that you started with. Ideally, line it up so that the x terms are matched up. So x cubed should go with x cubes, x squared should go with x squareds, because that'll make the next step a lot easier, because what you're going to do is now subtract that from all of this. So I like to put brackets around it to remind myself that I'm subtracting the whole thing. I'm not just putting a minus sign on this, because I see it all the time where people will try to do the subtraction. They'll go x cubed minus x cubed equals 0. That's nice and easy. Then they'll go x squared plus 2x squared and completely forget that there's still a negative that needs to be attached to it. So to remind myself, and hopefully to remind yourself, put brackets around the thing, the whole thing is being subtracted. So how this should actually read would be x squared minus 2x squared, which is why you end up with the minus x squared. The rest of this is zeros, so anything minus 0 is just itself, which is why those are just going to drop down. That sequence is going to be repeated a bunch of times until we finish. Before I go any further then, is it fair enough what's going on there? Any of those steps need to be clarified further. Sick. So we're just going to do that. What you'll notice is that we got it from a cubic to a quadratic. How do we repeat everything? This becomes our new starting point. So we treat this n bit here as if it was here now. So once again, biggest terms get divided by each other. This divided by that gets you negative x. You're going to tack it onto the end of the top bit. This top bit here is referred to the quotient specifically. And it'll be our end result of our division. We've done our division of the leading terms. Now when you multiply through, just remember you're only grabbing whatever the result was through the denominator. You're not taking the whole numerator and chucking it through, you're just taking whatever this bit was specifically. That's a bit I also see people get confused with a bit, because they see the whole denominator and they think, oh, I should also do the whole numerator. Not quite. But it is an easy mistake to make but also identify, because when you get to this stage you'll very quickly realize something's gone a bit weird. But yeah, so multiply everything through, that's going to get you that. What you'll notice is if you're doing this right, the leading terms will always disappear. If you've ever made a mistake, there will no longer be there will be a leading term there, in which case you go back and figure out what the hell went wrong. Even in this case, right? Negative x squared minus x squared. Double negatives cancel out, leaving you with a positive. Again, double negatives here, which is why we go up a little bit, and once again it's going to drop down. Rinse, repeat, over and over and over again. And if it's done in the context of solving polynomials, this should always say 0 at the end. If it doesn't say 0, then something likely went wrong, because there would no longer be a perfect factor sequence like we were trying to get to. Now I do specify it's only a problem if the goal is trying to solve the polynomial. If the goal is just perform the division, you could have any number here at the end and it'll be fine. That number there is the remainder after division. This bit here is the part that is perfectly divisible. This part here is what's remainder, what's left over. So to have factors, you want to have 0 remainder, right? That's why it's a bit of an issue. But again, if it's just saying, hey, divide these two things and find the remainder for me, that number can be whatever it ends up being. This works the exact same even if it isn't linear on the bottom. There's no real issues there. What you'll find is that it only gets slightly complicated in the sense that because you're doing x cubed divided by x squared, it goes down a bit faster. Instead of having like a quadratic up there, you have a linear up there now. And when you place your terms, they don't line up unless you manually make it line up. So for instance, the x cubes, they're perfectly fine. You might want to put a plus 0 in here and then a plus x over here. That way, when you're doing a subtraction, you're just doing vertical lines and subtracting whatever's vertically opposed. It doesn't look as neat though. So, if you are doing it this way, just keep in mind you want to do these, but don't try to subtract x from x squared. You want to subtract it from the minus 14x. The other weirdness that comes with x squareds or anything higher power is your remainder term. Your remainder isn't necessarily always going to be a number. There could also be variables involved as well. The reason why there would be variables involved is because of this sort of mismatch between how many steps you're taking in that division, right? You're going x cubed divided by x squared. You're getting to linear pretty quickly or at an accelerated rate. So there's two stopping points. One is when you get a constant, just any value, like minus 25 on its own, for instance. The other is when you try to do the next loop, if you get a fraction as your result with x in the fraction in the denominator spot, that is also grounds to stop. For instance, you would do minus 15x divided by x squared. That comes out to be a fraction with x on the bottom. We're not going to deal with that. We just want basic whole numbers or variables in here, nothing else. So that is also going to be a stopping point. And you can see how that's a bit shit to have, because now when you multiply both sides by x squared plus 1, you've got all of this in brackets and then this in brackets. This one's easy to solve in brackets. This one, you're not going to get anywhere with it. So that's why if you do get stuff like this in the context of solving polynomials, it's likely the case that something went wrong. But as I said again, if it is just doing polynomial division, perfectly fine to have that. So that's where it's headed. Lots of steps, but you are really just repeating 3 steps over and over until you get to some end condition there. I don't know how effective it is going to be for us to try and do one together, because usually I would need you to basically say each of the steps out loud there. Let me know if you feel like it'd be good for me to do one and wrap it up that way, or what I could do is I could just move on to the next thing and just sort of introduce you to that, if you like. Yeah, next thing, certainly. So what we just saw there was the concept of, yes, we can do polynomial division. It's a thing we can use maybe for solving polynomials. One glaring problem. If I just have that cubic and I don't know that it's divided by this linear, where the hell did that come from? Like if I'm just told to solve this, well, how am I going to get this so that I can get my factorization? That's where this comes in. So remainder and factor theorem. Largely speaking, before getting into any details, it is a quick equation that can figure out the remainder after any division. So we saw this division here. We saw that we had to do a big process to figure out everything we needed to figure out. If all we cared about was the remainder at the end, we don't have to do that whole division. We can just do a quick equation. Now, it does have restrictions. You can only do it if there is a linear divisor in there, but it is much quicker. Simply put, you take whatever the function is you're trying to divide, and as long as you know what you're trying to divide it by, which we'll get into in a bit, plug in the terms from that. So linear is ax plus b. A goes in the bottom, b goes in the top of that fraction as a negative. F of x is the polynomial that you're trying to divide. Trying to divide. So basically, in this case, your b is going to be -2. So now it's going to become -2, and the a is going to be 1. That's where those coefficients come from. Chuck it in there, simplify, simplify, simplify. When all is said and done, without doing any long process, we know there's a remainder of 6. Or in other words, that is not a factor. X minus 2 is not a factor. You're looking for 0 here, because if you have 0 remainder, you know you have a factor. We're going to hit time here. In fact, we've just hit time now. I will very quickly say how you actually find that factor, which is, okay, in all these cases, I've given you the factor to test whether it's a factor or not. How you find it is you look at the end right there. The end of that term has a constant. In this case, it's +6. What you do is you list all the factors of that term, both positive and negative. So, 1 and 6, 2 and 3, all those will make 6, and they all split out together. And then you test those. If you get 0 on any of those, you found the right combination that you need. Now, we don't have time to then dive into the rest of everything, but that's how you start working towards getting your actual linear. I've got a whole sequence on this, by the way. I think, as far as these group classes are concerned, I think we're ahead of polynomials right now. Let me just double check where we're at. Yeah, we're not going to touch on polynomials for a while after this. So as far as if you want to do more polynomial stuff, let me know for the Friday classes if you can do those. We can do those in review. Or look at the past recordings on when we did polynomials. It'll be in the class 1 curriculum for past recordings. Those will be the main ways that you can get polynomials related stuff here. Or if you, actually I don't think you guys have grabbed a copy of the resource pack that we have. I also have little scripted lectures that are like 10-15 minutes long on each of the key questions, basically teaching out of these notes as well. So those are the main ways we could follow up on the polynomials related stuff. Yeah, I'll see you next time that you show up, or if you have any questions. Easy. And yeah, you can message me on like the school chat, or if you have my number, any of that's totally fine. Just let me know. Happy to support. Have a good one. Thanks.